Here we'll introduce a shape called an ellipse. But first, which of these shapes is a circle? To review, click down here instead. Right, this is a circle. Now, an ellipse is a shape you get when you stretch a circle. So let's stretch this circle, and so here's an example of an ellipse. You could also call this an oval, but ellipse is the mathematical name. You can also get an ellipse by squeezing a circle like this. Squeezing it further gives us an even skinnier ellipse. So next, take a look at these four shapes. Which of these are ellipses? Great, so these are both ellipses. Next, take a look at this ellipse. Let's put a point at its center, and let's also draw a line segment through the center. If we look at all the different lines passing through the center, this one is the longest, and it gets a special name. It's called the major axis. So take a look at this ellipse. Which of these line segments is the major axis for this ellipse? Exactly. Here's the major axis for this ellipse. So now here's our ellipse from before. This is the major axis, and here's the shortest line segment that passes through the center. It's called the minor axis. So for these ellipses here, which of these green line segments is a minor axis? Excellent! This is a minor axis. This segment happens to be a major axis, and this segment is neither, so it doesn't get a special name. Next, take a look at these three ellipses. Here are their major axes, and here are their minor axes. Do you notice anything about how these axes are related? Perhaps something about the angles between them in each ellipse. Precisely, so these are all 90-degree angles. In general, the major and minor axes of every ellipse are always perpendicular. Now one more thing. Again, here are the major and minor axes. Each half of the major axis is known as the semi-major axis. Semi is a prefix meaning half. And similarly, each half of the minor axis is known as the semi-minor axis. So suppose you have an ellipse whose minor axis is 30 meters long. How long is its semi-minor axis? Now it's time for you to make your own ellipse. You can drag these two yellow dots to change this ellipse's semi-major and semi-minor axes as well as the orientation of the ellipse. So for this ellipse here, this is the semi-major axis because it's longer, and this is the semi-minor axis because it's shorter. When these two axes have the same length, this is actually a special kind of ellipse that you saw at the beginning of this lesson. What's the specific name for this shape? Nicely done. So a circle is actually a special kind of ellipse whose two axes have the same length. So this is no longer a semi-major or semi-minor axis. Each of these is a radius of the circle. Suppose you have a circle with a radius r. What's the area of this circle? You can find the area of many shapes by counting the number of unit squares inside them, but the curved edge of the circle makes counting these squares quite challenging. So let's come up with a formula for the area of a circle. First, do you remember the formula for the circumference of a circle? If not, click here to review. Right. The circumference of a circle, that is, the length of the curve around the circle, equals 2 pi times the radius. Now let's find the area of this circle. We'll find the area by cutting up the circle into a few slices and then rearranging the slices. So here we've cut the circle into 6 slices. Let's rearrange them so that they alternate which direction they're pointing. The area of this new shape has the same area as the circle. But finding the area of this shape is also tricky. Let's again cut the circle up into slices, but this time let's make many slices. Again, let's rearrange these slices so that they alternate which direction they're pointing. Now here's a shape whose area we might be able to calculate. When we cut the circle into really narrow slices and rearrange the slices like this, what shape do these thin slices appear to form? Exactly, Arranging the slices this way looks like a parallelogram, or actually a rectangle, as the slices get thinner and thinner and these angles in the corners become right angles. So the thinner we slice the circle, the closer to a rectangle this shape becomes. Just keep in mind that all of these purple lines, like this one over here, have the same length as the circle's radius, and the circle's circumference, which is green over here, is now split into two equal halves along the top and bottom edges of the rectangle. So here's the rectangle we get when the slices are incredibly thin, and this rectangle has the same area as the circle. So let's find the area of this rectangle, which means we need to find the lengths of the sides of the rectangle. First, what's the length of this side over here in terms of r? Don't worry, this is not a trick question. Exactly. This side has the same length as the radius, so its length is r. And because this is a rectangle, this side over here also has length r. Now remember that the circumference, which you said has length 2 pi r, is split up into two equal halves along the top and bottom sides of the rectangle. So what's the length of this side down here in terms of r? Right, this side has length pi times r, and this side up here also has length pi times r. Together, their combined length is 2 pi r, which is the circumference of the circle. So now that you've calculated the side lengths of this rectangle, what's the area? Nicely done. The area of a rectangle is its length times its width, so that's pi r times another r, or pi r squared. And as we said, this rectangle has the same area as this circle. So the area A of a circle with radius r is pi r squared. Let's try taking these formulas for circumference and area for a spin with a sample problem. For a circle with radius 4, calculate its circumference and area. Let's find the circumference together and then you'll find the area. So circumference equals 2 pi r and the radius is 4. So that's 2 times pi times 4, which equals 8 pi. And pi times 8 is approximately 25.1. So rather than counting the unit squares inside a circle, try using this formula to find this circle's area. You can express your answer in terms of pi, or you can approximate the area as a fraction or decimal instead. Here we'll introduce Cavalieri's principle, which is a way to find the areas of certain kinds of shapes, like this one here. But we'll start off with a rectangle. And let's say the base of this rectangle has length b, while the height has length h. What's the area of this rectangle? If you're not sure, click down here to review. Right, the area of a rectangle equals its base times its height, so that's b times h for this rectangle here. Now Cavalieri's principle says that when you cut a shape up into lots of thin slices and then move those slices around, you're not changing the area of the overall shape. So let's cut this rectangle into a few slices. And now let's rearrange the slices so that they're slanted like this. The lengths b and h have not changed. b still represents the length of the base down here, and h represents the vertical height of the shape that's perpendicular to the line of the base, meaning this angle over here is 90 degrees. Now the area of this new shape is still the same as the area of the rectangle, because we didn't change the size of any of these slices. This shape is not a quadrilateral since it has way more than 4 sides. But if you squint your eyes a little, what kind of quadrilateral does this shape kind of look like? Exactly. This shape looks like a parallelogram, except these sides are pretty jagged. We can make these sides a little smoother if we were to cut our original rectangle into thinner slices. So let's double the number of slices and then arrange them so that they're slanted again. Now this looks even more like a parallelogram, and it still has the same area as our original rectangle. If you imagine the slices getting thinner and thinner, then this shape turns into a parallelogram. So according to Cavalieri's principle, what's the area of a parallelogram with base b and height h? Exactly right. So a parallelogram with base b and height h has the same area as a rectangle with base b and height h, because you can rearrange really thin slices of the rectangle so they form a parallelogram. Let's say what Cavalieri's principle is a little more precisely. At the base of the parallelogram, the width, meaning the distance from one side to the other, is b, and the same goes for this rectangle. The distance across is b. You can think of these orange lines as really thin slices of these two shapes. Now let's look up and down both figures. They have the same height, and they also have matching widths everywhere along their heights. When this is true, the two shapes must have the same area, and that's Cavalieri's principle. Let's take another look at that peculiar shape from the beginning, and let's try to find its area. Let's say the vertical height of this shape is 7, and the base over here has a length of 6. If you look carefully at this shape, you can see that the width is 6 at every point along the height. So what's the area of this shape? If you're not sure where to get started on this question, just click over here. Exactly. You compared this shape to a rectangle with base 6 and height 7. These two shapes have the same height, and everywhere along the height they have matching widths. And so by Cavalieri's principle, these two shapes must have the same area. The rectangle has area 42, and so the funny-looking shape over here must also have area 42. Again, here's Cavalieri's principle, and let's use it for one more question. Here are three shapes, and they all have the same base and the same height. Let's also draw in widths at various places along the height for all three shapes. Now remember, if two shapes have the same height and matching widths everywhere along the height, then they must have the same area. So which two shapes here definitely have the same area? Right, these two triangles have the same area. Sure, all three shapes have the same width at the bottom, but if you look near the top, the two triangles still have the same width, while this curved shape over here is wider. The two triangles have matching widths everywhere along the height, and so by Cavalieri's principle, they must have the same area. Now it's your turn to demonstrate Cavalieri's principle. Here are two rectangles, and notice they have the same height and matching widths everywhere along the height. In this interactive, you can drag around different parts of the blue rectangle. These two shapes still have matching widths everywhere, so Cavalieri's principle says they still have the same area. Try playing around with these other shapes, a triangle, a circle, and a pentagon. You can use Cavalieri's principle to find the areas of some really weird-looking shapes like this one here. After you've played with all of these shapes, try answering the question up here.